Hello everyone. In the third part of this video series, I'm going to walk you through how to simulate two-phase boiling in Fluent in a microchannel setup. So here we have our microchannel model in open up. The channels width are about 200 micrometer. The height is about 1.5 centimeter, and the length is about 10 centimeter. So there is a microchip element is attached to the microchannel cold plate here that we're going to apply the heat load at the top of this microchip, and then we have already filled the volume with the fluid, and we're going to have inlet and outlet boundary conditions defined for this fluid. The name sections, a quick overview. We have fluid input, fluid output, and chip power chip power phase, where we apply the heat flux on top of this element. The other important thing is the shear topology. So there is a shear topology between the chip and the cold plate, and also the fluid and the cold plate has a shear topology definition. We're going to switch to watertight geometry workflow here. So here is the model imported into a Fluent meshing environment. We're going to follow through all the standard method as this meshing method that is as described in part 2 of this series. So if you would like to look at have a better idea of like how we measure geometry, it is described in part 2 of this video series. So I'm not going to go through this, and I'm going to go directly to this Fluent interface after I'm done with meshing our body. Okay, here's our model imported into the Fluent. We have the fluid inlet and fluid outlet identified with the microchip on the top. We are in the domain. We can check the quality of our mesh. So it is done. There is no errors for mesh. We can move on to physics tab. Under the general, you can see the general model equations. We are using a G parameter to define the gravity. Operating condition, if you look at the operating condition, we are using the Bosnian-esque parameter for operating temperature. We are using a user input for variable density, like as discussed in part 2 of this video series. We are defining a series of expressions for operating density, operating pressure, inlet temperature. If we move to the viscosity model, we are using the standard K omega steady state. And if we move to the multi-phase tab, we are using mixture, no velocity for the phases. We have two phases, water and vapor. Here we are using water H2L material that we are going to define it in the material, and for the vapor we are going to use H2O vapor. Phase interaction, we are using the RGB table to define the surface tension coefficient. There is one mass transfer from water to vapor. We are using evaporation and condensation model, so it is the Lee model with the semi-mechanics mechanistics boiling. These are the parameters we are using. For saturation, we are using the RGB table. And this is the length scale of our problem. We are setting it up to 1 millimeter basically. So we keep everything else the same, and we can close this. For the material part, we have each water, liquid, and vapor loaded into the model. For the solid, we have aluminum and copper. So we can assign this material to our cell zones. So if we go to the cell zone, under the fluid, if we open up the fluid cell zone, we are using the mixture rule. For the cold plate, we are assigning aluminum. So if we move to the microchip uh, cell zone, we are using again aluminum there, and you have the option to use copper or aluminum. Again, this is kind of a test setup to evaluate the microchip, like this microfluidic type of cooling. So this microchip is made of copper as a heating element. So I'm going to assign a copper to it. So next, let's move on to the boundary conditions. On the boundary conditions, we need to define the input and output. So it's going to be a velocity input boundary condition. So if we look at the fluid input, we are using our named expression to define the inlet velocity. And thermal, we have the inlet temperature. For fluid output is going to be a pressure boundary condition. We are using again the name expression outlet pressure, and for the thermal is outlet temperature. Uh, and for the heating phase, we are using this chip power phase, and if we edit it again, like we're using an expression wall heat flux. Okay, the boundary condition. Everything else is being handled by Fluent. So we are ready to move to the solution. But before that, I just want to show you the name expressions that we have here. We have inlet temperature, inlet velocity defined. Operating density is 0. Outlet pressure is a formula which is based on the density of the mixture, and again, our heat flux is set up to this value to start the simulation. Okay, before we start, we go to the solution. Solution method, as we see, is coupled, and we set the gradient to this square cell based, and we put all the parameters, the solution method to second order upwind, except the volume fraction. And the pseudo time method is global time step. Okay, controls. These are the controls we are using right now. For definitions, we are adding some definitions here. As we can see here, we have defined a set of definitions. These are for post-processing and also monitoring our solution, so we can see the convergence of these values as the solution progress. Residuals, we are going to monitor all these residuals. Iteration is up to 1000. and we're gonna store everything. Convergence criteria is none, and hit OK. So we are ready to start the problem. We're gonna go to the initialization tab. We're gonna initialize the problem. We're gonna initialize the problem first. One thing that I want to mention is I have requested two animations for volume fractions of vapor. One at the plane at the midsection of this cold plate, and one at the with the view of the fluid only. So we are going to look at these animations once the simulation is done. Okay. So let's initiate again from the fluid input one more time. Now we go to the run calculation tab. Time scale factor of 0.2. We need 1000 iterations, and we keep everything else the same. So we start the calculation. We can look at the residuals and see how the problem is being converged. This is the view of the residuals. As we can see, the problem is progressing. All the definitions that we had in the model is being calculated, and we can see the variation. This is pressure in the inlet. This is temperature of outlet, vapor volume fractions, like all the important parameters that we are looking after them are being calculated. This is also a view of the contours that we have requested for movie generation. So this is the volume fraction of the vapor. As you can see, like we have a lot of vapor generated across the surface of the microfilms. And this is another view of this is at the center plane in middle of the microchannel geometry, and we can see how the vapor is being generated across the fin. So I stopped the simulation after 24 iterations. We can take a look at the residuals. They're kind of stable. If you look at our contours, like in the mid plane, you see there's a lot of vapor is being generated. It's kind of a vapor blanket, so it's not good for design. We may run into thermal runout in this case. From the top view, you see like the vapors are being generated and propagated through the flow. We're going to take a look at the movie that we generated. Inlet pressure is keep rising because we are creating a lot of vapor in the flow. Outlet temperature is raising up because of the vapor we are generating in the outlet. This is volume fraction of the vapor in the middle plane is going up. So to get to a steady state, we need many more iterations. Now let's take a look at the animations that we have created. This is in the plane view. This is volume fractions of the vapor. So you can see that we are generating a lot of vapor here, and from the 3D view, we can see like we are hitting up all the fins, and like we probably is going to run into thermal runaway in this case. So our design needs modifications to address this issue. So this was the end of our video today. I hope this has been very helpful. So if you have any questions, please feel free to reach out to us at SLAC Center for Simulation and Reliability Engineering. Thank you.